So, dear friends, we were trying to develop an expression for maneuvering point. You know that we took two examples. One was steady coordinated turn, another was pull-up. And doing that, we found out expression for pull-up pitch rate Q is equal to G by V into n minus 1, and for steady coordinated turn Q was equal to G by V n minus 1 by n. What is n? N is the load factor, and you could see that if I want to have a pull-up with a given load factor n at a given velocity v, then this expression tells you how much pitch rate you need to generate. Okay? And how to generate that pitch rate? You generate through elevator movement. Okay? And how this pull-up maneuver is done? You know that I am going as a cruise, then I pull up, I go for given elevator deflection, and I go in a radius, and depending upon the value of n, I need amount of q through this expression for a given speed v. Right? Same story is true for steady coordinated turn. The question was how much elevator I should in addition put to get these maneuvers. And what we realized was, suppose the airplane is going in a cruise, so for that there is some delta E required for trim, which I know how to find out through delta E equal to delta E naught plus d delta by dCl into Cl. Now he has to give an additional input, elevator input, to go for a pull-up. And this pull-up, what we realize is, if I see the tail, then as it is going for a Q pull-up, then there is an additional relative air velocity the tail will see, and that induces angle of attack, and that is roughly, you can write QLT by V. We have our LT is the distance between CG and AC of the tail. We have already done that. And then we ask a question, how much delta E I need to give in addition to whatever delta is given for cruise, so that this additional angle delta alpha t, which will generate an additional moment, pitch down moment, that doesn't happen. So I have to neutralize that. To neutralize that, how much delta E is required? We derive it like this: delta alpha t, which is Q LT by V, this equal to 0, because I know tau is nothing but d alpha t by d delta E. So this tells me per unit deflection of elevator how much change in the tail angle happens. And from there I found delta E required is minus Q LT by V into tau. And we also said that we need to take care of the fuselage portion ahead of the wing, and roughly it's not bad approximation if I just add 10% to whatever delta E I'm getting through this approximation. So this is basically delta E required to go for the maneuver. Please remember, it is in addition to whatever delta E was given for trimming the airplane for a cruise. Okay? So what happens? Now, if I try to find out what is the delta E required, we showed that, and that was given by delta E, you know that delta E naught plus d delta E by dCl trim into Cl trim. This is required for the cruise. Then because I am doing this maneuver, so this additional delta E will come. So this is minus 1.1 Q LT by V. So I know that the delta E required for a pull-up, I have to go like this: delta E naught plus d delta E by dCl into Cl trim minus 1.1. In place of Q, I should put the expression for Q pull-up, which is, here tau will come, which is G by V n minus 1 Q into LT by tau V. So if I write this expression, I will get delta E pull up equal to delta E naught plus d delta E by dCl into Cl minus 1.1 G by V square, and this is tau. This is n minus 1 into LT. So LT I can put it here. This we have done last time, right? And we also realize what is this CL trim now, because I am going for a pull up. So lift equal to NW. So CL equal to NW by half rho V square S. So that is the CL value here, which is NW by half rho V square S. You could see from here, this is delta E pull up. You could see here, if I am going for a cruise, that will be n equal to 1. So this term vanishes, and n equal to 1. So this is the typical CL for n equal to 1, the level flight. Okay. So this is the expression, right, which we have done in the last class. So let me continue with pull up. Let me write this expression: delta E equal to delta E naught plus d delta E by dCl into, for Cl I write NW by half rho V square S. This is nothing but Cl equal to NW. This is Cl expression, right, for lift equal to NW, which we have been expert now. So minus 1.1 G LT by tau V square n minus 1. This is typically delta E required for a pull-up with a load factor of n. Right. Now let us see what is d delta E by dn. That will be what? That this man goes. So this will be d delta E by dCl into W by half rho V square S minus 1.1 GLT by tau V square. D delta by dn, so this n, so 1 it's here, and this n vanishes, so this is like this. Now let us focus here. We define stick fixed neutral point, that is x and p, as, or sometimes np, this is as the CG location at which d delta E by dn is equal to 0. What was stick fixed neutral point? It was CG location at which dCm by dCl is 0. What is maneuvering point? We define as CG location at which d delta E by dn is equal to 0. Right? So you can easily find from here the value, because the CG location is somewhere here, sitting here. Remember, d delta I by dCl is what? That is xCg minus n naught. So it will be there. So we will now do a simple algebraic manipulation and find out what is the location for maneuvering point, right? And I am saying we are now discussing about maneuvering point stick fixed. When I say stick fixed, you all understand by now that we are not allowing the elevator to float. That is, give deflection and hold it. Okay? There is no floating tendency. So whatever angle I have given for an elevator, it is fixed there. Generally, since elevators are mounted through a hinge, there is a floating tendency of the elevator which will come in the next class, next or 1 or 2 classes. However, you remember we are allowing anything happens, so we say stick fixed. So now what happens? If I put d delta E by dn equal to 0, d delta E by dn equal to 0, we get an expression 0 equal to d delta E by dCl into W by half rho V square S minus 1.1 GLT by tau V square. So from here you could see d delta E by dCl. D delta E by dCl is nothing but xCg minus xn naught by Cm delta E. Or if we are not able to comprehend, remember d delta E by dCl was minus dCm by dCl by Cm delta E, and dCm by dCl was minus static margin, so I write this static margin means x n naught neutral point minus xCg. This is divided by Cm delta E, so this is d delta E by dCl, so which I have written, taken the sign appropriately, it is like that. And of course these are all non-dimensional with chord, so I put it like this, bar. Always I put the bar with the understanding these are non-dimensionalized with the chord. So now what happens? I put it here. So I get expression 0 equal to dCm by dCl fix, right, into W by half rho V square S minus 1.1 G LT by tau V square. Of course here this is a Cm delta E, because I know d delta E by dCl is minus dCm by dCl by Cm delta E. So minus dCm by dCl fixed by Cm delta E into W by half rho V square S minus 1.1 G LT by tau V square. This is equal to 0 means straightforward you could see dCm by dCl fix equal to, from here you could see this is equal to, let me write the expression because unnecessarily we are wasting time, GLT rho Cm delta E by 2W by S. Once you solve this equation, you can easily show that dCm by dCl fix is minus 1.1 GLT rho Cm delta E by 2W by S. I will advise you to do yourself these things, otherwise you will lose insight. What is our aim? Our aim is to find the maneuvering point. And what was the maneuvering point? It is that xg location at which d delta E by dn is 0, and we have put d delta E by dn equal to 0. From there we got this relationship, and now what is dCm by dCl fix is xcg minus n naught equal to minus 1.1 GLT rho Cm delta E by 2W by S. Can you tell me how to get the maneuvering point expression from here? I repeat, maneuvering point is that CG location at which d delta E by dn equal to 0. By putting it to 0, by doing some algebraic manipulation, we have come to this stage dCm by dCl fix equal to minus 1.1 GLT rho Cm delta E divided by 2W by S. So now I get expression xcg minus n naught equal to this. What is this xcg? This xcg is corresponding to the case when d delta E by dn is equal to 0. That is how I got this expression. Because it is 0, so from here I got this expression. So this xcg corresponds to case where d delta E by dn equal to 0. That is how we have derived. Hence this xcg becomes the maneuvering point, nm, stick fixed. Sometime I am missing this bar. Please understand that whenever I am putting in dimension, they are non-dimensionalized with chord. So please be careful. Okay. So what we have got from here? We got a very interesting relationship that nm minus n naught, nm minus n naught equal to minus 1.1 G LT Cm delta E and also rho divided by 2 W by S, or I can write nm equal to n naught minus 1.1 G LT rho Cm delta E by 2 W by S. What is the message you are getting now? You know that Cm delta is negative. So this term, this side with minus sign become positive. Therefore, if this was n naught stick fixed, okay, then nm is greater than n naught. Because this is minus, so minus minus plus, so nm is greater than n naught. That means nm will be aft of n naught, which is correct or not? Nm should be behind n naught, means this is a more stable case, and we know as it goes for a pull-up, there is a delta alpha t which tries to give a nose-down moment, so apparently it becomes more stable, right? And that is why indeed this expression makes sense, because apparently more stable means the neutral point or the maneuvering point should be aft of stick-fixed neutral point. That is, if I bring the CG close to n naught, it becomes statically unstable. But as far as maneuver is concerned, I can draw the CG up to this point where d delta E by dn will be 0. That is why this is maneuvering point and this is a stick-fixed neutral point. This is stick-fixed maneuvering point. This is a wonderful expression, and generally we do experiment and try to find out this through some experiments. I'll tell you how to do that. Okay. Only my worry to all of you is that so many expressions we write, you should not lose insight. Please, every time ask yourself why I am writing all this expression, what I am going to find out. This whole lecture today, what is going on, we are trying to find out the maneuvering point. What is the maneuvering point? It is that xg location at which d delta E by dn becomes 0. Okay. So let us do a little bit of more algebraic manipulation. It may help us to give some insight. We started with d delta E by dn equal to minus dcm by dcl fix by cm delta E into 2 w by s rho v square minus 1.1 g lt by tau v square. This again I can write a little differently. D delta by dn I can write as minus 1 by v square 2 w by s by rho cm delta E to 1.1 g lt rho cm delta E by 2 tau w by s plus xcg bar minus n naught bar. Nothing great we have done anything. We have just taken this common. So since in the first this term w by s was not there, so I put w by s. So I get xcg minus n naught. Now what I will do, we know from this expression n naught equal to nm plus this term. Where from we got this expression? By putting d delta E by dn equal to 0. So this was the maneuvering point. So now there is n naught lying there, so I will replace n naught by nm plus 1.1 g. So this will further I will write as minus 1 by v square 2 w by s by rho cm delta E and then 1.1 g lt rho cm delta E. You please do yourself 2 tau w by s, then xcg bar. For n naught I am writing nm plus this term, right? So since this is a minus sign, minus n naught, so it will be minus nm and minus 1.1 glt rho cm delta E by 2 tau w by s. Nothing great I have done. Please, I repeat, n naught I have replaced by this expression. N naught equal to nm plus 1.1 g lt rho cm delta E by 2 w by s. And what has happened by doing this, this gentleman and this gentleman get cancelled, and you get an expression d delta E by dn equal to minus 1 by v square 2 w by s by rho cm delta E into xcg bar minus Nm. This is a very interesting expression. All these expressions you could derive because we have assumed that neutral point is a location at which dCm by dCl is 0, and here we assume that maneuvering point is that location at which is that CG location at which d delta E by dN equal to 0. Based on that, by doing some sort of algebraic manipulation, we have come to this expression, and it can be verified that if xCg is at maneuvering point, then d delta E by dN indeed becomes 0. It also tells us d delta E by dN largely depend upon wing loading and inversely with the control power and inversely with the v square. This is very, very important from pilot field point of view. Okay? Let us summarize what are the things we have learned. See, we know now the definition of N naught. Sometime I have written it as x N naught. This is called neutral point. Neutral point stick fixed. Then we have understood what is Nm, which is maneuvering point. Stick fixed. This is one word every time I am saying stick fixed, just for the initial introduction. Let me tell you that if this is the elevator here, because this is a hinge line, with any alpha, it will have a tendency to float because there will be pressure distribution, and if this resultant is behind the hinge line, it natural tendency to float this way or that way depending upon where is the location, because if this friction is too less. But when it says stick fixed, I am not allowing this to happen. That's the meaning of stick fixed. The stick is fixed, nothing, no such floating is allowed. We will see actually it floats, then what is how to model the problem. That is a different issue. But when I say stick fixed, means stick is fixed, nothing, no floating is allowed. Now the question comes, how to determine N naught bar and Nm bar through flight test. Let us first talk about N naught bar, which is a stick fixed neutral point. How do you define a stick fixed neutral point? Define it is that CG location at which dCm by dCl is 0. Now you also know from the equation that d delta E by dCl trim, right, is equal to minus dCm by dCl by Cm delta E. So if neutral point is that CG location at which dCm by dCl is 0, I can equivalently say, because dCm by dCl is here, this becomes 0, this is never 0. So I can equivalently define neutral point is that CG location for which d delta E by dCl trim is 0. This is an approximation, because you know this expression is an approximate expression, but from experimental point of view, this is good enough, right? Why this is important? Because when I do experiment, I can easily measure delta E. I can calculate CL trim, right? How do I measure delta E? You know, if this is an elevator, when the elevator rotates, it is connected to a potentiometer shaft, rotary potentiometer, something like this. So as this man rotates, this shaft also rotates, and then it develops some potential difference, some voltage, and that voltage I can calibrate and get what is the amount of deflection of the elevator. So it is easy to measure, and CL trim always, you know, you can do it because if lift equal to weight, then CL equal to 2 W by S by rho V square. So if I know what altitude I am flying, I can get the density. If I know what is the speed I am flying, I can know this v square, and what is this w by s, weight of the airplane, and the wing area. So this is also, I can compute easily. Right? So to calculate neutral point through experiment, I will be using this concept that it is the CG location at which d delta E by dCl trim is 0. So how do I do this experiment? Let us understand that. So we are saying it is N naught is that CG location approximately for which d delta E by dCl trim is 0. What I do? I go for an altitude, let's say altitude. I also note down the outside air temperature because I need these two information to calculate the density of air at that altitude. Right? This is required for calculating rho at altitude. Okay? Now what I do, I cruise. I go to the altitude, I try to cruise at particular V, let's say V1, V2, V3, V4, V5. And then ensure that I have trimmed the airplane because I'm cruising, so I'll measure the delta E, say delta E1, delta E2, delta E3, delta E4, and delta E5. So I repeat, I will go to an altitude, I'll fly at a particular speed and note down what is the elevator deflection given for trim. Similarly for V2, what is delta E2, like that up to V5, what is delta E5. I can take 6, 7, 8, 9, 10 readings, whatever is possible. But before I do this experiment, remember, what is our aim? Our aim is to see that what is that CG location at which the aircraft becomes neutrally stable or d delta E by dCl trim is 0 equivalently. So when I go for an experiment, I should note down what is the CG configuration of the airplane. This is extremely important. So what you do, well, suppose you have 5 passengers are going, so you will take the weight and find out the CG location. Right? And let's say this reading is for one combination of XCG1. Then second batch will go, you will also generate similar reading V and delta E, right? Which may be corresponding to XCG2 location. So different people, different weight, they can swap here and there and fly for different CG location. Like this, XCG3, XCG4, XCG5, various combination of CG you will fly, and you will trim at different V1, V2, V3, V4, V5. Okay. Once you have done that, if I take first case for a combination, another combination XCG1, one group, so I can plot for that group what is delta E and what is the CL. Now the question is, how do you find the CL? You can answer, okay, I'm cruising. We are trying to find out N naught. We are cruising, and when I cruise, that means CL equal to 2 W by S by rho V square. Since you are taking all this measurement, you know what is the value of CL for a corresponding V. So this is CL1, this is CL2, this is CL3, like this, using this relationship. So you have delta E, which you have measured. You have CL1, which through V, using this relationship, I got CL1. For XCG1 combination, that is for one group of people, the total aircraft CG is, let's say, XCG1. So I will be plotting this, and I'll get a graph d delta E by dCl, let's say XCG1. Correct? So similarly, I take another case for XCG2. Again, I plot delta CL. So there's the graph is like this. Third one may be like this. Fourth one may be like this. Depending upon where is the XCG2, XCG3, XCG4. Now, what I should do, I will take the slope of this line and I cross plot d delta E by dCl as the slope versus xCg. Clear? So I take the slope, I take the xCg location, so this is the point. I take this slope and this is the CG location, so this is the point. Like this I'll get points, I join them and it cuts at a point on the x-axis. So this is the point at which, this is the CG location at which d delta by dCl trim is 0. So this is the neutral point, stick fixed. Clear? Let me repeat. We want to find out a naught, which is the CG location for which d delta E by dCl trim is 0. Now how do I do that? I know how to measure elevator deflection through instrumentation based on potentiometer, rotary potentiometer. So I go for a cruise, I note down the altitude, I note down the outside air temperature, because this will be used to find the density at that of air at that altitude. Right? I fly in a configuration, let's say 4 people, and we have a fuel in the tank, so we find out what is the xCg location for that configuration. I call it xCg1. Then I cruise at V and select and check what is the delta E elevator required for trim. Similarly for V2, similarly for V3, V4, V5. So I have series of V1 delta 1, V2 delta 2, like that, V5 delta 5. Now once I know what is V at say V1, I need to know what is CL1, because I want to find this delta d delta E by dCl trim. So CL trim I can find because I know I am cruising. So CL is given by 2W by S rho V square. So I use this V, I use this rho, then I find what is the CL, and then I plot delta E versus CL for an xCg1 configuration. I draw a straight line. Similarly for xCg2, xCg3, xCg4, maybe xCg5. Now what I do, I take the slope, so d delta E by dCl, and this corresponds to xCg1, so I mark it here. Similarly here, 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 so all this point, then I join and extrapolate, and where it cuts, this is the xCg location at which d delta E by dCl trim is 0, so this is called the neutral point stick fixed. This is the way to find out experimentally. Okay? Now, once neutral point is stick fixed, you know how to find experimentally. We need to also know how to find maneuvering point stick fixed through experiment. So now we'll be discussing how to find out experimentally the maneuvering point. Okay? What is maneuvering point? It is that CG location at which d delta E by dN equal to 0. Right? What is N? N is the load factor. And delta E is the elevator deflection. Okay? We can do 2 maneuvers, but we will be actually doing safer steady coordinated turn. And what is that? I go like this, I bang the airplane and turn like this without losing the altitude. And we know in this process, the load factor is given by N equal to 1 by cos phi. So whatever bank angle I am maintaining, I am still maintaining the coordinate turn. From the bank angle, I'll see from the cockpit what is the bank angle. Immediately I know what is the load factor, because I know N equal to 1 by cos phi if the airplane is taking a steady coordinated turn without losing any altitude. So indirectly I am getting the value of load factor through bank angle, and bank angle I see from bank angle indicator, which is housed in the cockpit. So now how do I plan it? So what I do, again, I go for an altitude, right? Then I'll note outside air temperature, and then I take xCg1, and this is one group of people, they are going for one experiment. So they will go for a steady coordinated turn, and they'll note down what is the V, what is the phi, and what is the delta E. Right? Clear? So how do you get phi? Phi get from the bank indicator. Bank indicator is there in the cockpit. From there you can find bank indicator. By knowing phi, immediately you can calculate what is n, because n is equal to 1 by cos of phi. So now you have delta I, you have n for a given xcg1 location, right? So again I will do that. What I will do, I will plot delta E versus n. I will get some value, and this is xcg1. The second batch will go and do exactly the same, but that will correspond to a different CG location, because different people will be sitting, different weights. Sometimes what you do, initially you go 5 people together, then you put 2 people together, then you put only one student in the front, so that there is a difference in the CG location. There is a variance in the CG location. So you can do like that. Maybe this is xCG2, this is xCG3, maybe xCG4. Like that you will get different data points. Now what we do, again you recall, maneuvering point is that CG location at which d delta E by dn equal to 0. So I will find d delta E by dn from the slope of this line, which will be straight line approximately. So I put d delta E by dn, and this is xCG. So again, d delta E by dn 0. For different CG location, I'll get points. If I join them, this is my NM. This is the CG location at which d delta E by dn equal to 0. So this becomes my experimentally determined maneuvering point. Is this clear? You could yourself check why d delta E by dn for a given xCG location be negative. See the expression of d delta E by dn and put the appropriate sign of the derivatives, you will find the answer. Okay? And I'm sure you will be able to do it. I may ask such questions for your assignments. Okay, thank you very much.